Hi, this is Dr. Jivikas Paul. In this session, we'll discuss about the secant formula and Perry's formula and problems related to them. So, till now we have discovered whenever the load is coming actually on the column, how to calculate the buckling load. That we have seen using Euler's and Ranking's theory. Now, for eccentric type of loading on the column, which formulas we will apply? That is secant formula and Perry's formula. First of all, let us discuss secant formula for eccentric loading. So this is the column, length of the column is L and load is P coming on column. It is eccentric load. The load is acting at a distance of E from this point, from the column. Okay, now this is the secant formula. Sigma max is equal to P by A plus P into E into secant LE by 2 effective length by 2 under root P by EI by Z, where sigma max is maximum stress, P is eccentric load on the column, A is area of cross section, E is eccentric distance, LE is effective length, E is Young's modulus, capital E, I moment of inertia, Z is section modulus I by Y is distance from centroid. Okay, it is a problem on this secant formula. A column of circular cross section is subjected to a load of 120 kilonewton. So if you see a column, it is a circular cross section, okay, and the load coming on it is 120 kilonewton, right? The load is parallel to the axis but eccentric by an amount of 2.5. So what is this distance? E, small e, 2.5. So P is 120, small e is 2.5. The external and internal diameters of the column 60 and 50 mm. So external diameter of this column is 60, internal is 50 respectively. If both the ends of the columns are hinged and the column is 2.1 meter longer, length of the column is 2.1 meter long, 2.1 meter. Okay, now so both the ends are hinged. So when both the ends are hinged, we know that effective length is L. Then determine the maximum stress in the column. We need to determine maximum stress in the column due to this load, sigma max. We have that formula. We can apply directly this formula to calculate sigma max, maximum stress. Take Young's modulus equal to 200 giganewton per mm square. So this is a given data. Load is given as 120 kilonewton. Convert to newton into 10 power cube. E is 2.5 mm. Convert to meter. 2.5 into 10 power minus 3. So it is 60 mm. Convert to meter. 0.06. This is 0.05. And when both the ends are hinged, we know that LE effective length equal to actual length equal to 2.1 meter. So E is given as 200 giganewton per meter square. So into 10 power 9, giga means into 10 power 9 newton per meter square. So sigma max equal to, this is a formula. In this we need, P we know as 120. This we need to find pi by 4 capital D square minus D square, area of cross section. So this is the area in meter square. Then I pi by 64 d power minus d power 4. This is the value of I. Then Z, I by Y. I we have calculated here. I divided by Y. Y is d by 2. Y is d by 2. What is d? External diameter? 0.06. Okay. So I by, we will get this one, Z. Now what is this? Let us calculate this part. Secant LE by 2 under root P by A equal to secant LE, we know 2.1. 2. This we know. This we know, this we know. If we calculate, this will get in radians. So into 180 by pi, we'll get this one. Okay. So sigma max, substitute all these in the formula. All these things in the formula, you will get this answer. So using the same formula, let us see other problem. From the following data of column having circular cross section. So we have a column with circular cross section. Calculate the extreme stresses on the column section. So what are the extreme stresses on the column? There is a load coming on it. Okay. So what is a load coming on it? It is given here, right? Calculate the extreme stresses on the column section. We need to calculate the maximum stress. Also find the maximum eccentricity in order that there may be no tension anywhere on the section. So here we have two questions. First question is we need to calculate sigma max for the given data, and second question is to find also find the maximum eccentricity, to find eccentricity E value when there is no tension in the section. Two questions are there here. Okay, Right. So external diameter is given, diameter is given, length is given, length of the column is given. Okay. So eccentricity is given 2.5, load carried by column 200 kilonewton, and both ends are fixed. So when both ends are fixed, L equal to L by 2. E is given 94 GPa. Okay. These are the given data. Capital D is given, convert to meter. Small d is given, convert to meter. Length 4 meter, P 200 into 10 cube Newton, and E is given as this one. LE is L by 2. E is 9 into giga, so 10 power 9. So we have secant formula. Here we have to find A first. This is area. Then we need to find the I value. Okay, I value. Then P is secant LE by 2 under root P by E. If we calculate, we'll get this value, this one. Then Z if we calculate, we'll get I by Y. So Y is D by 2. Okay, now what is D? External diameter is given as this one, 20 to 10 power minus 2. Okay, and as this is your Z. Okay, now next, maximum compressor. Substitute everything in this formula. Substitute all the values are there, you can substitute directly. Then you can find sigma max. This is the first question. Next question, what is the maximum eccentricity when there is no tension? So when there is no tension, this becomes 0. That means P by A is equal to P is secant L by 100 P by A divided by. So this is the condition when there is no tension. When there is no tension, this is the condition. So substitute all the values here. Here we don't know E value. Okay, here E we need to find. This E is not this E 2.5 centimeter. This E we need to find when there is no tension. Okay, so when you substitute all the values here, E is unknown, and you can find E in this way, 40.2 meter. So when eccentricity is 40.2 mm, then there is no tension. That is the meaning. Now let us see another method. Perry's formula, sigma max by sigma naught minus 1 minus sigma as a naught by sigma equal to 1.2 E y divided by k square, where sigma max is maximum stress, sigma naught is direct stress, E is eccentric load distance, K is radius of gyration, Y is distance from centroid, sigma E is stress due to eccentric load. So let us see a problem on this Perry formula. A compound stanchion 3 meter long is made up of two channels ISJC 200 and two 250 mm by 10 mm plates riveted on each flange. Find the maximum load that can be applied at an eccentricity of 20 mm from the axis YY. The permissible compressive stress is 80 Newton per mm square. Assume hinged ends moment of inertia of the compound section YY axis may be taken as 4.5 into 10 power 7 mm power 4. So this is a Perry's formula. So sigma max is given as 80 Newton per mm square in the question. Sigma naught is not given. E is given as 20 mm and Y is capital D by 2. So here it is 250. Okay, 250. So 250 by 2. Then sigma E is the Euler's stress equal to Euler's load by A. We know formula for Euler's load, pi square E I by L square. Okay, this is your sigma naught. Substitute all the values, E I L square, everything. Then sigma E is equal to 1153. Then how to find this K square? This is K square. Okay, R radius of gyration may be denoted by R, small r or K. Okay, anything. So I by A. This is I and this is A. Okay. So K square equal to I by A. Substitute everything in this formula. Sigma max, sigma naught is unknown. Sigma E, Y, everything. Okay. Then we got sigma naught as this one. The safe load equal to stress into area. So this is your safe load. This is answer. Thank you. And one more concept is column analogy method. What is column analogy method? It is a method used to analyze indeterminate structures. So to analyze, column analogy method is used to analyze indeterminate structures like continuous beams, fixed beams, frames and other arches also. It is ideally suited for computing stiffness and carryover factor in beams and frames having variable cross sections.